So in this unit, we're going to start covering structured system process requirements. So here we're going to talk about how to do modeling to show how how business processes work. So previously we talked about requirements, and with requirements, we were trying to understand, with gathering requirements, trying to gather all of the information that we need to understand a system and a process. Now that we've gathered all that information, we have to try to demonstrate our understanding of the processes, the business processes, using some modeling techniques, which we're going to start talking about this week. We're going to cover this week the structured modeling processes, or the structured technique for modeling processes. And the structured technique is going to use some different syntax than you would have in UML or object-oriented. But in this course, I'm going to cover both ways of doing modeling. So we're going to talk about both methods. But we're going to start with the structured process modeling. It's a little bit simpler. It's a little bit easier to learn. But it does have some limitations. We'll talk about that once we get to the object-oriented. So first, we're going to understand the logical modeling of processes by looking at data flow diagramming. Then we're going to learn about the rules for data flow diagramming. I'm going to show you how to decompose data flow diagrams to lower level diagrams and talk about that concept, how we balance data flow diagrams to ensure consistency across different diagrams, and how to use data flow diagrams as a tool to support the analysis of information systems. So, which I think is going to be kind of obvious how we would do that. And then finally, we're going to discuss modeling the electronic commerce applications that are in our textbook, as well as using logic tables. So we'll talk about using decision tables to model logic. Sometimes we have complicated logic. It's helpful to use a logic table to show the decision process. Now, all of this stuff that we're going to talk about, we've, previously in the course we were talking about planning. Last time, in the last presentation, we started talking about analysis. And here we are still in the analysis phase. So when we did our requirements determination, that was part of the analysis phase. Now structured or requirements analysis is also part of the analysis phase. So these process models that we're going to create are part of the analysis phase. So basically, a process model is going to graphically represent the processes that capture, manipulate, store, distribute data between a system and its environment and among system components. So again, we're going to show how to graphically show how data moves through a system, and some of the ways that we manipulate that data as it goes through a business process. So this is going to require what we gathered in the requirements phase. So all of that gathering of information that we did previously, we're now going to use to help translate that into diagrams that we can use to demonstrate the workflows. So we're going to use that to model processes and data structures. And we'll get to data structures later on. That's going to be in another unit later on. So when you create these models, some of the outcomes, the deliverables of this phase will be context level data flow diagrams, which I'll talk about, but they're basically going to show the scope of a system. Then you have data flow diagrams of a physical system to adequate detail, and then you're going to have data flow diagrams showing the current logical system, so we can understand logically how the system works. Once we have the current physical and logical diagrams or data flows, then we're going to create a data flow diagram of a new logical system. And this is going to be sort of, we're hopefully will identify ways to improve the business process, right? And we're not thinking about technology yet, right? So we're not actually designing anything yet. We're just thinking about the business process itself. So we're not thinking about what can a new system do for us, what new technologies might we have. We're kind of thinking independently of technology at this point. We're just looking at the logical flow of information through a current system. And then we're seeing what can we do to streamline this? What can we do to improve this process and make it better? And then once we do that, we can create a physical, let me get my PowerPoint here. We could do a physical physical DFD design, which we'll talk about later on. All right, so a data flow diagram, or a DFD, is a graphic that illustrates the movement of data between external entities and the processes and data stores that are within our system. So we have external entities that are outside of our system, and then inside our system we have processes and data stores. So external entities we usually call a source or a sink in data flow diagramming. Specifically, I'm going to be talking about the GANE and SARSON method of doing data flow diagramming, but basically a source or a sink is anything outside of our system. All right, so when we make these diagrams, you're going to have a context level diagram, which is going to show you from a very high level. Basically, all we're going to show in a context level diagram is what the sources and sinks are. In other words, what systems and people and roles interface or interact with our system. And then we're going to show our system in the middle. And that's pretty much it. So a context level diagram is very simple. It shows our system, and it shows the various things outside of our system that are going to interact with the system. And we're going to show data flows of what they're using the system for. And I'll show you an example of this in a little bit. So it's a pretty straightforward diagram. And then we have our physical and logical data flows, which will be a little bit more descriptive, and then our narratives, which describe in words what's happening in those diagrams, especially if you have a particularly complicated data flow. Now, the method that we're going to talk about in this course is the GANE and SARSON method for doing data flow diagrams. And again, this is a structured technique for data flow diagramming. There are other data flow diagramming techniques like the object-oriented and UML style modeling, which we're going to talk about later on. And I think those are very important. It's really important to talk about those. But before I get to those, I want to cover kind of the older structured modeling techniques, which we're going to see here. And there's some things that I really like about the structured modeling techniques. Obviously, the object-oriented stuff that I'm going to talk about later is very important and commonly used in industry. And I think GANE and SARSON method may be much less commonly used in industry today than it was, say, 20 years ago or 15 years ago. But there are definitely some things that GANE and SARSON has to offer us, and things that we can learn from modeling data flows using GANE and SARSON. And one of those is that the rules that GANE and SARSON sets up for us when we do diagramming force us to think about data flows in a certain way that ensures that we're properly decomposing and understanding the system that we're designing or that we're analyzing. So that's definitely a good thing. So the four symbols that you'll find in the GANE and SARSON method, you can see here, are the data flow, which is the arrow. You have a data store, which is that sort of half rectangle, the rectangle with the missing side. Then you have a process and an interface. And these are just the symbols that they use. Now, I should tell you that the GANE and SARSON method is not codified in any formal standard. So you'll see a lot of variation in these symbols if you use some of the tools that I recommend in this course. So if you're using something like Microsoft Visio or Draw.io, which I gave you a video for on how to use Draw.io, you use that with the project management portion of this course. If you look at any of those tools, you're going to see some variation in what these look like. When we talk about object-oriented modeling later on using UML, you'll see there's a lot less variation in what you see me use in our PowerPoints versus what you see in those tools, because those symbols are standardized, right? They're all codified in a standard that's well understood. Where GANE and SARSON, it's a little bit older. It didn't really have any widespread standardization, so again, you'll see some variation here. So the mechanics for GANE and SARSON, a data store is how you show data at rest or a physical location that data is stored in. So when you're not using data, it goes into a data store. I don't want to use the term database because it doesn't necessarily have to be a database. There are lots of different technologies that we can use to store data. So we just call it a data store. In many cases, it is a database, but it doesn't necessarily have to be. A process is where we work with the data. So anytime we're performing some kind of an action on data, if we're changing it, if we're storing it, if we're distributing it, if we're moving it, whatever, that's going to be a process that does that. So anytime we're doing something with data, that's going to be a process, so that's going to be a verb. And I'll talk more about some of the grammar here in a little bit. And then finally, the source of the sink is the origin or destination of that data outside of our system. So these are things that are happening outside of our system, or these are people, organizations, other systems that are outside of our system. Anything that interacts with our system is going to be a source or a sink. All right, so let's talk about some of the rules for data flow diagramming. So first, when we talk about a process, so if you recall, there's the symbol for a process. No process can have only output. Because if you have only output from a process, so if you have a process sitting there and it's only producing output, that's a miracle, right? That's you can't produce something from nothing. A process must get something, do something with it, and then pass it to something else. Okay, so you can never have arrows just coming out of a process and never coming in. Now, and by the way, so what you see here at the bottom, that would be valid, where I have data both coming in and going out of a process. If you see data, if you draw a process and you only see data coming out of a process, what you've drawn is possibly a source or a sink, because they can produce the data. They can provide only output, for example, and that would be valid. But a process cannot do that. Next, A process cannot have only inputs, right? That would be a black hole. So if we have data only going in and nothing ever comes out, then that's not a process. That's just the data going into a delete, into the recycling bin, right? So we can't have data just going in to a process. Again, you can have data going in and going out, but it can't just go in. And once again, if you find yourself looking at a process and the process only has data coming in, chances are what you've actually drawn is a sink, right? So a source is stuff coming out, which is external to our system, and a sink is stuff going into some other system. And by the way, many of the external things around our system are both a source and a sink, right? They're both using the system and the system is using it, or getting things from the system, or you're putting things into the system. So again, if you have a black hole, chances are that black hole is probably really just a sink. And I want to pause here for a second. This is one of the things that's nice about the GANE and SARSON data flow diagramming technique, is it forces you to think about things like that, right? So if we're thinking about a process and we're trying to follow the rules but we can't, it forces us to realize that, you know what, this isn't actually a process that I'm looking at. This is actually a source, or this is actually a sink. It's actually something completely different. Okay, so that's one of the nice things about GANE and SARSON. So when you create a process, it's going to have a verb phrase label. So it's doing something, right? So it's updating something. It's transforming something. So verb noun, right? So it's a verb noun phrase. So it's doing something. Okay, it's taking some action on something. All right, so those are the rules for a process. The rules for a data store, first, is if you have two data stores, you cannot move data directly from one data store to another. A process has to do that. So this is where you need to have a process in the middle. So you can't draw an arrow from one data store to another. It must go through a process in order to get there. So that's rule number one with data stores. Likewise, data cannot be entered directly by a source, right? So if you have a source and it's going directly to a data store, that's not allowed. You have to have it go through a process. So the interface, or the source, has to use the process to get the data into a data store. So if you're drawing your diagram and you have a source or a sink, it cannot go directly to the data store. Instead, and here's the other example, right? You can't have a data store sending data directly to a source, or to a sink rather. Again, you have to have a process in the middle. So basically, I can summarize by saying that anytime you have a data store, it has to go through a process to get to either to another data store or to a source or a sink. They cannot talk directly to one another. You can think of this in programming terms as well, right? If you have a data store, which is a relational database management system, some of you are taking an RDBMS class, right? You might be taking a database class, and you're learning that language to interact with the database. Could you imagine an end user having to learn that language and interact with the database? That would be very unusual, right? So you have to have something that can do that on their behalf, like a user interface, which would be considered a process. All right. So when we create data stores, you're going to use a noun phrase label. So it's going to be something, or something or someone or something like that. Okay. All right. So finally, we have our sources and our sinks. Well, not finally. It's the second to last symbol we're going to talk about. But so we talked about our process, our data store, and now our source or our sink, which are external to our system. Okay. So they have a noun phrase label, a source or a sink. So first rule is that a source cannot go directly to a sink. Okay? Think about this for a second. If you're drawing your diagram and you have information going from one external entity to another external entity, and it's not going through the system, do we care about that? Not really, right? That's happening outside of our system. We don't need to waste our time thinking about that. That's outside the scope of what we're designing. That's really, we're not involved in that communication, so we don't need to worry about that. So, and sometimes students get confused with this because they'll say, well, what if my user needs to go ask another user before they put something in the system, right? Again, that communication, while it's important to understand it, it's not directly related to the system, so we don't put it in our diagram. You can certainly mention that in a narrative or something like that, but there's no reason to diagram that. So anytime you have data coming out of a source or going into a sink, it should be coming from a process, or it has to come from or go to a process. Remember, it can't go to a data store either, right? Okay, So data flow rules. So the data flows themselves. The arrows cannot be double-ended. You always have to split them into two different arrows. And you'll see an example of what a data flow is. The data flow describes the actual flow of data from one of these things to another, right? So if a process is storing a customer record, right, we would have customer record going to the data store. Now, you may be thinking, well, that process can not only send things to the data store about a customer, but it might also be getting things about a customer from a data store. Well, you would have to show that as two different arrows. One arrow for stuff going in and another arrow for customer data coming out. Okay, so we cannot have double arrows. We have to have them these two separate arrows. So a fork means that exactly the same data is flowing to multiple places. So if you have data flowing out of a process going to two different places and it's two different sets of data, that would be invalid. You can't do that. You have to draw two completely separate arrows to show that. However, if it is exactly the same data, right, if it's both this exact same thing going to two different processes, then it would be acceptable to draw a fork. So you can do that. So again, a fork has to be exactly the same data. It cannot be two different things coming out of that process. You'd have to draw two completely separate data flows to do that. And the opposite, of course, is a join. And just like our fork, if you're doing a join, you can't have two different types of data joining together to form maybe a different data. Like let's say we have the phone number coming from one process and the email address coming from another process, and that's coming together for customer contact information going to another process. You can't do that. They have to go to a process separately, and then maybe another process could put that data together and send that to another process. So you could put something in the middle. Or if it happens to be the exact same data, then that's okay to show that as a join, if that is. So if I have the phone number coming from two different processes for some reason, maybe sometimes it comes from one process and sometimes another, but it's the exact type, the exact same data that I'd be getting from either of those processes, then it would be okay to draw that as a join. So joins and forks are really not that common, as you can guess, because of some of these rules. Normally we're drawing these things independently. So data cannot flow directly from where it came. It has to go through a process. What would be the point, right? So data should never come out of a process and go right back into a process. That doesn't really make any sense in the GANE and SARSON data flow diagramming. Instead, it has to go through another process before it gets there. Okay, so that, chances are, if data is leaving our process and coming back in, something is doing something to that data. Well, that would be another process. Otherwise, we wouldn't need to draw it, right? Because that data would already be in a form that we needed. So again, you cannot draw that sort of unary, data coming out and coming right back in without going through some other process. All right, so data flows are going to have a noun phrase label, meaning that it is a thing that, again, is doing something. So some guidelines for DFD. First, we want to make sure we have completeness. In other words, we have all the components necessary. Okay. Second, we were going to make sure we have consistency. I'm going to show you an example of this in a few minutes, but we start with what's called a context level diagram. That shows all of our sources and our sinks in our system. Then we're going to decompose the system into its component parts, and that may include data stores, it may include other processes, and we have to make sure that all of the inputs and outputs from our sources and sinks that were in our context level diagram are exactly the same when they go into deeper level diagrams. And I'll show you an example of that in just a few minutes. As far as timing goes, DFDs never start and never stop. There are more appropriate diagramming techniques to show temporal events. In other words, things that happen in sequence, right? So if we want to show sequence, there's a different diagram for that. It's called a sequence diagram. It's actually part of the UML and object-oriented diagramming techniques. But data flow diagramming really doesn't have any concept of timing. It's sort of a snapshot in time. There's really you can't really go to the diagram and say, okay, where did we start, right? There is no start and there is no end. It's just stuff happening, right? You can kind of start in your mind that process anywhere you want. There's no, it doesn't happen in one specific place. As far as iteration, we talked about the iterative nature of systems analysis and design, and this is one of those diagrams that certainly would have some iterations where you would have a draft of the first data flow diagram, and as you develop the additional decomposed diagrams, you might have to circle back and do them over again as it helps you refine your understanding. And that's one of the most important things about data flow diagrams, is they really help us understand the systems that we're diagramming, right? That's kind of the real point of doing these, is we're trying to understand what it is we're trying to do. And a data flow diagram is a great way to do that. It helps us get into the discipline of decomposing and deconstructing systems to see how they work, right? It sort of forces us to do that. Now, as far as how far we decompose systems, right? We start with this context level, and we're going to try to decompose a system into more and more parts to try to understand how it works, right? Think about a car. If you want to understand how a car works, you could take apart, you could open up the hood and look at the engine. But now that we're looking at the engine, well, how does the engine work? Well, now we can start taking apart the engine into its parts, right? And the question is, how deep do we go before we say, okay, I've got a pretty good understanding of how this works? And that's where this concept of primitive DFD comes in. When do we stop? And generally, it's best when you're designing a system, if you want to fully understand how a system or a process works, you're going to stop decomposing when you get to a process that is a single decision. So if you have a process where it's a single decision, a single data store, right? It all comes down to one single thing, then there's nowhere left to decompose that particular process. There's nowhere to decompose, right? But we have to try to decide, how deep do we actually go? And that's what we're talking about with primitive DFDs, is how deep do we go? And that's a design call. That's a sort of, that takes experience and, to understand how deep you need to go when you're looking at these things. Now, this is an example from your textbook. In your textbook, they have an example of a fast food shop, right? A fast, like a kind of a McDonald's style place. And in this, I think they call it Hoosier Burger in your textbook. But in any event, this hamburger stand, it has customers, it has the kitchen, and it has the restaurant manager, right? Those are our sources and our sinks. A customer is providing an order, right? Then our food ordering system is going to send that order to the kitchen. And it's also going to send management reports to the restaurant manager, and it's going to send a receipt back to the customer. Okay. Now, one of the things that students will always ask me when they look at this diagram, they'll say, Brian, you're missing something here. I've got an order coming from the customer to the food ordering system, and then I've got that order going to the kitchen. But what about when the kitchen is done making that hamburger? The hamburger has to go to the customer, right? So don't I need to show the hamburger going from the kitchen to the customer? And if you recall, when we talked about the rules for data flow diagramming, would we draw a line from the kitchen to the customer? Would that break the rules for data flow diagramming? And the answer is yes. And the reason this is important is because it helps you think about what's salient to your analysis, right? We don't care that the kitchen makes a hamburger, right? That makes no difference to me in my system. I don't care that a cook is going to make that hamburger and give it to a customer, and the customer is either going to like the hamburger or not like the hamburger, right? None of that really matters to me when I'm designing the system. All I care about is that the kitchen gets the order. After they get the order, there's nothing out left that the system needs to do except give the receipt to the customer, which can happen independently from the order. Okay? So, again, it forces us to think about what's important in our analysis. And again, making the hamburger is not really that important. So that's a pretty accurate design. Now, here we took, now let me go back a second. So 0, or the context level diagram, shows just the food ordering system. But there's a lot of stuff that happens inside the food ordering system, right? When a customer places that order in the food ordering system, lots of things have to happen in order for it to get to the kitchen. And that's where we decompose this a little bit, right? So there's some additional things that are happening here. So 1.0 shows that we receive and transform a customer food order. And while one copy is going to the kitchen, right? So that process is sending that order to the kitchen. It's also sending the goods sold to the update goods sold process, and it's also sending the inventory data to the update inventory file process. And then update inventory is updating the inventory file data store. The updates goods sold file is updating the goods sold file. And then both of those have a process. So there's also a process that's pulling information out of our data stores in order to give it to the restaurant manager, right? So they can have some reports. So again, you can see how that process is pulling that stuff out of D1 and D2 in order to provide it to the restaurant manager. So now we have 4 processes. So we decomposed our system into these 4 component processes. Now, one thing I want you to take a look at here is, let me step back. Notice we have 4 data flows in our food ordering system that are coming out of into or out of our system. So there are 4 ways that our sources and sinks are interfacing with our system. There's customer order, receipt, food order, and management reports. Those are the only 4 things coming in and going out of our system. There's nothing else on here, right? Now, when I go to the next level, notice that I still have those 4. Even though there's a lot more stuff going on here, even though I decomposed this, I decomposed that context level diagram, I still have the same data flows coming in and out of my system. There are no invented or new processes. There's no additional source or additional sink. If I found myself, and this is where we get back to that iterative process, if I found myself adding an additional source or an additional sink, or I found myself adding an additional data flow, let's say we do this and it turns out, let's say I decompose this and I say, well, wait a second, the kitchen staff not only is going to make that hamburger, but when they're done making the hamburger, they go into the system and they have to say that the hamburger has been complete, it's been made. And that's what triggers the, somebody to go get the hamburger, right? Well, the system is mediating that, right? The system has to catch that message coming back. So I might add that data flow coming from the kitchen back into the system. I would have to go back to my context level and add that data flow from the kitchen to the food ordering system. And that's what balance is all about, right? That's the consistency and balance that I was talking about. Now I could decompose this one more time, right? So look at 1.0. Let's say receive and transform customer order could be decomposed again, right? Now, looking at that, the 1.0 has customer orders coming in, and then it has food orders and receipts coming out. So when I decompose that, notice that now this is 1.0. So now what we've sort of done is we've taken our microscope and we focused in on 1.0, and now we can see what's inside 1.0, right? It's kind of like biology class when we can see an organism, but when we get the microscope out, we can see that it's made up of other organisms like cells and bacteria and so forth. That's what we're doing here. We're zooming in and getting a closer look and seeing the component parts. So now I can see that process is made up of an additional 5 processes that make that happen. But notice we still have our balance here, right? We have customer order data coming in, we have the food order going out, and we have the receipt going out. Now you might be saying, Brian, wait a minute, there's inventory data and the goods sold data, but that also is coming out over here, right? That's going to process 2.0 and 3.0, so it's okay to show it in this other diagram. I still have balance. I can trace back those outputs and the inputs. All of that can be traced back to previous diagrams. So I still have my balance, and again, I'm showing it in much more detail now. I could also decompose 4.3, right? So take a look at 4.0. Let's go ahead and see what that would look like decomposed. So here's 4.0 decomposed. We have aggregate data coming in, then formatted data goes to the print manage reports, and then we get the management reports, right? So we've decomposed that process a little bit as well. Now again, these are some textbook examples. I could show you some examples from previous students in this course. This is an example of a context level data flow diagram that was done by one of my classes, gosh, almost a decade ago. I had a class more than 10 years ago that they said, hey, we want to look at creating a system for parents and teachers communicating, right, outside of the school, right? Some kind of system that will allow parents and teachers to communicate. And this was what they came up with. They said, okay, how do we communicate? How do parents and teachers communicate with one another? And they came up with these different data flows that would describe that interaction between parents and teachers and the different ways they interact. So this would be a context level, right? Because we have the parents, the teachers, and the administrators are involved in the process. And then we can see there's a process in the middle, and I can decompose that process into component parts, right? So we have the parent that's logging in and then doing stuff, and I'll talk about login later. We don't always really, care about login, but in any event, there's things that happen inside the system. This is probably not the best example because these students clearly are missing some things here, right? Because if you go back, it's not balanced with this original one, right? So here we have a parent that interacts with the system, but I don't see all of those different interactions with the parent and the teacher, right? So here I see the parent should be able to view attendance, communicate with the administrator, communicate with teacher. They should be able to get the grades, get disciplinary reports, but here all I see is login, right? So this is lacking that balance that I talked about. So that this particular group of students also, they kept decomposing and they got to something like this, and uh, and they kept going and tried to do the best they could to create a data flow diagram. But again, I just want to give you kind of an example of what students have done, and of course these are not the best examples. Hopefully you guys are going to give me much better examples. They're going to follow the rules. They're going to show that they're going to have that consistency and that balance that we talked about. So finally, I wanted to talk to you about some other types of data flow diagramming. I talked um, about using the GANE and SARSON method. This is another data flow diagram technique from Krabel and Wetzel. This one I've never seen in the wild. I've used it before. I've tried it, just to see how it works. I don't want to go through all the rules for this because, I could take up a whole nother, 30 minutes. I've already been talking for 30 minutes, but I just wanted you to be aware that there are other techniques out there. So if you go out and get a job in the field, I don't want you to think that the only structured technique for data flow diagramming is the GANE and SARSON method. There are other methods you might see, and even when we talk about GANE and SARSON, there's even variations among GANE and SARSON, right? So GANE and SARSON came up with the symbols that you see on the right-hand side, but DeMarco and Jordan used the symbols on the left-hand side. But they basically have the same rules and they pretty much work the same way, but they just use variations in what those symbols look like. So it's important to realize that these structured techniques are really not standardized in any kind of well-known standard. There's just these academic papers that describe the best way to do these data flow diagrams based on some research and what thought leaders think we should be doing. But again, no one really has to follow these rules in the industry. Now later on, I'm going to be talking about object-oriented object-oriented modeling techniques using UML, and those are standardized. So those are well understood and standardized diagramming techniques, and with those you're going to have to follow some specific rules in order to use those for them to be correct. And no matter where you go in the industry, those will be relatively uniform. But again, data flow diagramming and the structured techniques is not as uniform. So as I talked about before, we're always going to start with that context level diagram, which is an overview of the system. It's going to show the system boundaries, right? So we're going to see that here's the system in the middle, and then outside of the system, we're going to show those external entities that are going to interact with the system. They're also going to show the information flows between the entities, those external entities in the system itself. So only one process system and no data stores will be on a context level diagram. It's going to be very simple, which we already saw with the Hoosier Burger example from your textbook. All right, so a level 0 diagram is a data flow diagram that represents the major processes in data flows. So this is where we're going to begin to decompose the system into its various processes, and now we can start to show data flows. So this was an example of a level 0 diagram. This is where we first start to decompose that system into its component processes. And then, so there's two DFD guidelines that are going to apply. The inputs to a process are different from the outputs of that process. Okay, so we have to be able to transform inputs into outputs. Objects on a DFD have to have unique names. Every process also has a unique name. So these are some of the rules that we've talked about. So I already talked about a bunch of these. These are actually from your textbook. I just wanted to show them to you real quick. Okay, and this is just the second page. Again, these are in your textbook, but this is what we've already covered so far. And then this is also from your textbook. This just shows you the rules for data flow diagramming that I talked about in the previous slides. But again, you'll find this in your textbook as well, but this is just kind of a brief overview of what these rules are. All right, so the decomposition. So functional decomposition is this iterative process of breaking the system down into more and more detail, as I was talking about earlier. So it creates a set of charts in which one process on a given chart is explained in greater detail on the next chart. So, when you start with that one system from the very high level, that's your 30,000 foot view. And then as you zoom in closer and closer and closer, you're looking at more and more detail within the system. You're decomposing it further and further and further. And you keep doing that until they cannot be broken down any further. And again, it's kind of a judgment call on exactly how far you go. But a level 1 diagram is the decomposition of a level 0 diagram. And a level 2 is a decomposition of a level 1. And a level 3 is a decomposition of a level 2, and so forth and so on. And as you go deeper and deeper into the diagram, you should be using a numbering system that shows what level you're on. So for example, here I know I'm on a level 2 because I see a decimal point, right? So 1.0 would be on a level 0 diagram, and a 1.1 would be on a level 2, a 1.1.1 would be on a level 3, and so forth and so on. So here we see a level 2 diagram because we see 4.3.1, for example. All right, so balancing, so there's this conservation principle, conserving inputs and outputs to a process the next level of decomposition, meaning that we cannot invent or remove data flows. They have to be consistent from one diagram to the next. So we can't all of a sudden at the level 3 diagram show some new input coming into the system. We have to be able to trace that input all the way back up to that context level diagram. And we can see clearly who is providing that information to us, either a process outside of our system, like another system, or it could be a person that's providing that information. But we have to be able to deconstruct, or we have to be able to, trace back to that context level diagram to see where that came from. If you find yourself adding those additional inputs and outputs, that means that we probably have either a misunderstanding on how the system works, or we've missed something in the previous diagrams that we have to add. So balancing means that the number of inputs to lower level DFDs equals the number of inputs of associated processes of higher level DFDs. So we should be able to trace anything through our entire DFD sequence of diagrams. So here's an example, right? So if we have data coming from a source going to a sink, we can't in another diagram show additional sources, for example, right? So we can't just invent some new source on the next diagram. If it's in the level 0, it has to be in the context level. And if it's in the context level, I should see it supported in the level 0 and any other level diagrams from which it's looking at data coming from that source. So data flow splitting is when a composite data flow at a higher level is split into different parts to go to different processes at a lower level. So the DFD remains balanced because the same data is involved, but is split into 2 parts. So if you have a split, it's okay to show that the composite parts of that split. So that is going to happen, So if you, and it's same with a join, right? So if you have a join, you can do the same thing. By the way, I called it a fork before, but it's the exact same thing, right? A split and a fork are kind of the same thing. So there's 4 different types of DFDs. You have the current physical, and then we have our current logical, which is going to show the physical aspects of the systems are removed, and it's just kind of how does the system work, right? Usually we start with physical because we kind of have a sense in the beginning of where data is, right? Where are things happening? It's good. It's easy to get this sort of conceptual picture in your mind when you have it in physical terms. But then once I understand the physical data flow, now I have to start thinking about the logical workflow. Logically, how does this work, right? I think a lot of us do that when we're doing analysis. We probably do it intuitively for the most part, but we understand the physicality of how it works, but logically, how does this work? And then once I understand it logically, how the current system works, this is where I can start logically thinking about what could be better. What improvements can we make? What are some additional things that we can add? What are obsolete functions? So what are things in the old in the current logical diagram that make no sense? Why would we pull that forward into a new design of the system? Maybe they're deprecated processes that are no longer needed, or maybe for whatever reason we don't need that process. And then once we do all that, then we can create our new physical model, which will show us the new physical data flow. So we start with the current physical, then we try to understand it better by going to that logical, and then we can logically lay out how the new system might work, and then that can pull us into a new physical model. So that's really kind of the point of doing these DFDs. And by the way, this is really the end game to these DFDs. What we're really trying to do with DFD, we're not diagramming these just for the fun of it, right? We're doing this because it helps us understand the system. That's the primary goal with DFDs is with complex processes and complex business processes, it's really going to help us understand how the process works if we use data flow modeling to do that. So some guidelines, completeness, it must include all the components necessary. Again, we're going to have consistency, the timing, right? Time is not very well represented on DFDs, which I talked about before. So it's best to draw them as if the system never stops, and it's never going to stop. We don't want to think too much about sequence. That's going to come later in some other diagramming techniques. And again, it's an iterative process. We're going to go through this process over and over again. And I talked about the concept of primitive DFDs, which is, how do we make that decision to stop decomposing the system? At what point have we decomposed enough, right? When you're looking at an object could be made up of other objects, and then those objects are made up of molecules, and molecules are made up of atoms, and atoms are electrons, protons, and neutrons. And then what comes after that, right? We really don't need to decompose much further than that. There are certainly some things that happen below that, but most of us that don't study quantum mechanics really don't care too much about what happens beyond that level of abstraction. All right, continue with these guidelines. So rules for stopping decomposition. When each process has been reduced to a single decision, calculation, or database operation, there's really nowhere to go from there. So that really makes the decision for you, right? If you've broken something down to a single decision, there's really nothing else you can do. When each data store represents data about a single entity, that's a good place to stop. Or when the system user does not care to see any more detail, right? They've seen enough. There's nothing else they need to see. You have a good understanding of the system, then you can stop. When every data flow does not need to be split further to show that the data are handled in various different ways. Or when you believe that you have shown each business form or transaction or display or report, all of the things we talked about in the requirements gathering phase. If you think you've shown all of that stuff, then maybe you don't need to go any further. Or if you believe that there is a separate process for each choice on all the lowest level options. Okay. All right, so in the next slide deck, I'm going to talk about how to use data flow diagramming and analysis in the analysis process, and I'm going to talk about logic tables.